So as I said, you do not need to copy down the whole problem or anything, but let's kind of work this together. Jot down some work on scratch paper in your notes. All right, so it says a gas occupies a volume of 0.25 liters when the temperature is 25 Celsius. What will be the volume of this gas when the temperature is increased to 85 Celsius? Well, the first problem, or the very first thing we need to do is figure out what equation this is. So we do that by looking at the variables, especially the variables that are changing. So this is volumes and temperatures. Is that Charles, Boyles, Gay-Lussac? Charles, right. So that's, oh, I don't want that color. So that's V1 over T1 equals V2 over T2. Next step, we need to check what's going on with the units. What units am I given? Are there units that I need to convert? And yes, there are, because these are Celsius temperatures. You can never use Celsius temperatures with gas laws. Got to convert it by adding 273, as we were talking about earlier. So I'm going to add 273 to the 25 Celsius, so that's 298 Kelvin. And then 85 Celsius plus 273. So you have to change it, or just the gas law just flat out won't work. They're only made to work with Kelvin temperatures. When you write it, it's not a huge deal, but with a Kelvin temperature, you're not supposed to write a degree symbol. You just write 298 K. So now it's just a matter of plugging stuff into this equation and solving it. And usually, oh, by the way, I don't think I mentioned this, but if you're unfamiliar with equations that have these subscripts, all that means is like a volume at two different times and a temperature at two different times. So typically what we do is we have V1 and T1 be kind of the starting temperatures and volumes, and then we have these be what it changes to. So in this case, the volume was 0.25 when the temperature was 298 Kelvin. And it says what will be the volume when the temperature is, so that means we're solving for that, when the temperature is increased to 358. So, all of these gas laws just require very basic algebra, like the very first algebra you learned back in 7th, 8th grade maybe. But some of us, it's been a minute, right, since we've done this kind of thing. So my suggestion to you would be to take a cross-multiplying approach in this particular type of equation. And I'll remind you that what you do there is, I like to think of it in terms of diagonals or like corners. So there's the diagonal that does not contain the variable. That's where you want to kind of start. And those are going to be multiplied together. So 0.25 times 358. And then you're always going to divide it by anything in the diagonal that contains the variable. So if we're going to make a new little fraction or dividing thing over here, the part that does not contain the variable is always on the top, and then the diagonal that does contain the variable is on the bottom. And so we just got to calculate this out. Now, significant figures, we're going to try to get that right. It's not a huge deal, and if you never understood or struggle with sig figs, I'd rather you just had too many significant figures or something rather than rounding incorrectly, as long as you're not too egregious with it. But in this case, since we're multiplying and dividing the same significant figures as the least significant figures, which would be 2, so I believe that comes out to about 0.30. Always got to remember our unit. You're going to get the same unit as you put into the problem. So the volume unit we put into the problem was liters, so we get liters as an answer. Questions about that one? Let's look at another one here. So a gas in a syringe is a volume of 30. Pressure in the syringe is 95.7 kilopascals. What will be the pressure in the syringe if the volume is decreased to 15? I think that's Charles, Boyles, Gay-Lussac. It is Boyles, yeah. Pressures and volume. So it's going to be P1 V1 equals P2 V2. And so once we do that, we look over the problem. Now, you can use any volume unit and any pressure unit you want to, They do need to be the same though. Like I couldn't use volumes in two different units on two different sides, but we're fine there. So we don't need to do any unit conversions this time. But that's always something you want to look at. So when the pressure is 95.7 kPa, the volume is 30. And it says, what will be the pressure? That means you want to know P2 when the volume is decreased to 15. So again, just very basic fundamentals of algebra here to solve this. But as I said, sometimes it's been a minute for some of us. One of the very first things you learn in algebra, whatever's being done to the variable side over here, we're going to do the opposite. So instead of multiplying by 15 milliliters, we're going to divide by 15 milliliters. And I'm attaching units to things, at least in this case, to show you that what happens is that the units do cancel properly if you're doing it right. They do cancel properly and give you the unit that you want, which is kilopascals in this case. So it's just 95.7 times 30 divided by 15. You get about 191.4, I believe. 3 sig figs is what we should have. So if we want a perfect answer, it's going to be 191. Questions about that? Let me ask you this. Try this. What if you just multiply 95.7 times 2? What's that? Yeah, it's the same. How come that works? I know what you're right. Yeah, I mean I know what you're saying. Yeah, it's because it's inverse, and that's probably what you're thinking too. It's an inverse relationship. So if you cut the volume in half, if you cut the volume in half, the pressure is going to double. That's the way it works. Or if you cut the volume down to a fourth of what it was before, it's going to quadruple the volume, or the pressure. If you double the volume, the pressure is going to go down by half. So it's always going to work that way. So if you were really, focused in, and you could have just realized, oh, I cut the volume in half, I should just double 95.7, and you could have gotten it that way. Let's look at another one here. Suppose a gas, an aerosol can, has a pressure of 0.87 atmospheres, a temperature of 15 Celsius. Suppose you decide to put the can in an oven. What will be the pressure of the can in kilopascals at a temperature of 225? Okay, so a thing like a can is going to have a more or less constant volume. It probably could expand a little, but... So we're dealing with pressures and temperatures here. This is a Gay-Lussac problem. Next thing to think about is the fact that we have these Celsius temperatures. We've got to change those to Kelvin. So always, always, always remember, we cannot use Celsius temperatures. So in this class, really just in any sort of science class where you're doing math, it's so important to pay attention to units that are being given and being asked for, because there's an issue here in that we're being asked for a pressure in kilopascals. If we don't think about that, we're going to give the wrong answer, because if I just use atmospheres, I'm going to get a pressure in atmospheres. So basically, I have a couple of choices here. I can either I can either convert the atmospheres right now to kilopascals, or I can work the problem in atmospheres and then change that answer to kilopascals. It doesn't matter. Let's convert it first, though, just for kicks. And so this is what we were talking about on Monday. And when we were doing this, people were doing really, really well. Right? Like, I'm talking, if there was 24 kids in the class, like 22 of them were getting these problems right. But what I've found is, it's one thing if I'm like presenting it to you there on a platter, like do this now. But sometimes people are struggling a little bit in the application piece like this. So the first thing we need to have is a conversion factor, which is what I was saying earlier. All you need to know is two things that are equal in both units. And that's why we're going to use standard pressure, and that's why we want to know what standard pressure is in various units. So we come up with our conversion factor. And again, I'm going to convert the atmosphere. So remember, when we're converting units using dimensional analysis, we're going to start with the thing we're trying to convert. That's always going to go there. We're going to make one of these train track things. I'm going to follow the what goes up must come down rule. So my atmospheres is going to go on the bottom, and the 101.3 kPa is going to go on top. So it's basically 0.87 times 101.3. Probably we'll keep it at 2 sig figs, so let's call it 88. And again, the reason that I'm doing that is so that when I put it into my equation, I'll get an answer in the unit the problem is asking for. So the pressure in the can is 88 kPa when the temperature is 288 Kelvin. Put it in the oven, pressure is going to go up. That's a K, doesn't look much like a K. And so I think it's about 154. Or 152. 152 is what I'm getting here. So kPa. Now, the perfect answer would have 2 sig figs, which should be that. And again, I would prefer that you don't even worry about the sig figs rather than maybe making a really bad rounding error, like rounding that number to 15 or something like that. But the best answer with correct sig figs is the bottom one. 2 sig figs. Questions about that? Some of these that I want to talk about. So starting with number 2. This is number 2 on page 4 of the mixed gas law practice handed out in class. So this is also a Boyle's law problem and very similar to number 1, but there is an issue because it gives 2 different units. That's not going to work. It gives on one side it gives a volume in atmospheres, and on the other side it gives a volume in millimeters of mercury. So we can use any pressure unit, but what we cannot do is use different pressure units. So we have to have an awareness of one of those, and we need to convert one of those. It doesn't matter which. Now, it is easier to convert the 1 atmospheres, but just for kicks, in case it wasn't exact, because that's standard pressure, but just for kicks, let's convert the other one. And so the way I'm going to do this is just like we did before, and it requires knowing that in millimeters of mercury, standard pressure is 760. So we know that this is true. 1.0 atmospheres is equal to 760 millimeters of mercury. And you just have to pay attention. There's a few problems in here where you might need to convert the units before you start. You always convert to Celsius temperatures, but so that means we're going to divide by 760. So again, you always start with what you're trying to convert. Figure out your conversion factor. What goes up must come down. So the 760 is in the bottom. And so therefore it's 0.25 atmospheres, and that's what I should use to solve it. Now again, I mean, the easier thing to do probably if you just realize, oh, 1 atmosphere, that's standard pressure, so I should just, I mean, it says right here that 1 atmosphere is 760, so you could also just recognize that the 1 atmosphere is 760 millimeters of mercury, but it's not always that, it's not always that obvious. So I wanted to show you what you might have to do sometimes. So then we can plug that in. Something else I want to mention is sometimes these problems will give you a little bit of extra information, okay? This is like real life. Real life, if you have to solve a problem, any kind of problem, whether it's a personal problem, math problem, engineering problem, any problem, you are not presented with only the information you need to solve the problem. You're presented with all the information in the world, and you have to sort through what you actually need. So it's part of critical thinking, I guess, to realize, oh, there's extra info in here that I don't need. How you can tell that you don't need it is if anything that remains constant is not relevant to the problem. Number 4 is an example of this. It gives volumes, temperatures, and pressures, and so some people get a little confused, but then it turns around and says the pressure remains constant, which means that pressure can be ignored. So have an awareness of that. And again, don't forget, like on number 3, you always need to convert the Kelvin temperatures. So like when you do number 3, you're going to have to convert those. So I'm going to give you, okay, so here we are, page 6, the page about combined gas law problems. The combined gas law is this. So as the name suggests, it combines all the gas laws together, or all of the 3 that we've talked about so far anyway. There are a few others. In real life, almost always, it's literally almost impossible for really only 2 variables to be changing. Almost always other things are changing as well. So on this page, and very often in real life, we'd have to use the combined gas law. It can be a little bit more intimidating. There's 6 variables. Sometimes with the ideal gas, with the combined gas law rather, it might be a good idea to really like line out the variables before you start. You can do this on the other ones too if you find this helpful, but I like to really line out the variables here to make sure, because there's more stuff to keep track of. So this one, it says 2 liters of hydrogen originally at 25 and 750 millimeters of mercury. So let's let that be all of our ones, right? So 2 liters of hydrogen, that would be a volume. Liters is a volume unit. 25 Celsius, got to change it to Kelvin. That's 298 Kelvin. And then a pressure of 750 millimeters of mercury. So that's all my starting point here, 750 mmHg. And then it says, are heated until a volume of 20 liters and a pressure of 3.5 atmospheres is reached. What is the new temperature? Okay, so when it says what is the new temperature, that means we're solving for T2. Volume of 20 liters. There is an issue here, though, in the fact that it's giving us a pressure in atmospheres now, and we can't, that's not going to work. So before we plug that pressure in, we're going to use our atmospheres to millimeters of mercury conversion, which is, there's 1 atmosphere for every 760 millimeters of mercury. So I'm going to do that so that my pressure units agree on both sides of the equation, because you cannot use different pressure units, which is 2,660. Okay, so we're going to put numbers in here. We're going to solve it. To some of you, it will seem, a little more intimidating to solve, but the same rules of algebra still apply, and all the same techniques still work. None of that changes. So let's plug everything in. The pressure is 750. The volume is 2. Starting temperature in Kelvin is 298. New pressure is 2660. New volume is 20. And we're going to solve for T2. Okay. So you could take a few approaches to solving this, but my suggestion would be we can still do cross-multiplying. Cross-multiplying still works. Cross-multiplying works with any number of terms, anytime you've got sort of this like two-fraction type equation here. So remember, I like to think of it as a couple of different diagonals. There's this one, the diagonal that does not contain the variable. And then there's this one that does. What you always do is you multiply all the ones that don't contain the variables, and those go kind of on top, if you will. And then we're going to divide by these ones that I circled in green here. Now, my suggestion in terms of how to actually compute this, what I see a lot of people do is they'll multiply all three of these numbers, and then they'll write that number down. And then they'll multiply these two numbers, and then they'll write that number down. And then they'll type this number into their calculator again. And they'll divide by, and they'll type this number into their calculator again. I don't think, that's definitely not what I would do. What I would do is I would just type this into my calculator exactly like this. Hopefully, we at least have a calculator that's capable of doing parentheses. That's all we really need. And in fact, you don't even need the top parentheses. You just need to have the bottom parentheses. If you don't put the bottom parentheses in, it will divide by 750 and then multiply that answer by 2, which is not what you want. The reason that you would do that is because, first of all, it's about 3 times as fast. But second of all, every time you like write down a number and type it into a calculator again, it gives you another chance to make a mistake. So you have much fewer chances to make an error if you just type in your calculator just one time. In fact, if I was doing this, I probably wouldn't even bother writing down this part. But make sure, so for some of us, half the battle is just getting into the calculator right and actually computing it right once we get to that point. You should get in the neighborhood of 10,500. It's about 10,567 you might get, which is extremely hot. And again, if we really want to be perfect with sig figs, we actually should probably do that. But if you don't understand that rounding, I would rather you just kept the extra sig figs. Questions about that? Let me help you a bit with number 2 also. Okay, so this is a combined gas law problem. So here's the thing about this one. So it says 10 liters of oxygen gas at STP. So we have to understand what it's saying. It's saying to you, we talked about that at the beginning of the period. That stands for standard temperature and pressure. So it's kind of a shortcut way of telling you the temperature and pressure. We know the volume is 10, right? It just straight up tells us that. So standard temperature is 273 Kelvin, or 0 Celsius, but of course we want to use Kelvin. And also standard pressure, it is 1 atmosphere, it's 101.3 kPa, it's 760 millimeters of mercury, but I want to use millimeters of mercury. If I scan ahead in the problem, I will notice that the second pressure is being given to me in millimeters of mercury. So I should definitely use millimeters of mercury here, so I don't have to convert anything. And then it says, what will be the new volume if the pressure is increased to 1520 And then it's 312. So, of course, again, change that to Kelvin. So whenever you see that STP, or at least in these kind of problems, we know that we can just replace that with the standard temperatures and pressures I was mentioning earlier. So then we got to plug in and solve this thing. So the standard pressure, that's 760, times my volume, which is 10, times standard temperature, or divided by standard temperature, which is 273. New pressure is 1520. Solving for V2. And again, we can still use cross multiplying here. The number of terms doesn't matter. Nothing, I don't know, sometimes people think you can't in certain situations, but whenever we have these equations like this, you can always do cross multiplying. The diagonal that does not contain the variable, those are the ones that end up being multiplied together on top. And then we're always dividing it by anything that's on the bottom. And again, my suggestion would be to type it in your calculators like that. But even if you don't have that, rather than that, especially like when you get some of these huge numbers, like you get in the combined gas law, you can multiply these, hit enter, get an answer, and do the dividing separately, which again saves you from having to write down numbers. So you could multiply all three of these. You could divide by 273, get an answer, and then divide by 1520. So that's another way to do it that stops you from having to write down answers and slow yourself way down. But you should get about 10.7. If we're getting that into our calculator now.